Welcome to day 22 of Math 111. Today, we're going to be working with Cuisenaire rods. You'll need your set of Cuisenaire rods from your manipulative kit. Before we begin, find your Cuisenaire rods and have them handy as we go throughout this lesson. This lesson involves finding the greatest common factor and least common multiple. We're going to begin with an activity with Cuisenaire rods. Before we begin, you'll notice that I have made a staircase out of the Cuisenaire rods. The graphics that I'm using today have come from a website called Braining Camp. The images are a little better than the pictures that I can take. The staircase lets us see the different colors and lengths of the Cuisenaire rods and how they compare with each other. First, let's talk about the colors. All of the colors are pretty obvious. The only time there's confusion is when we have the green. And you'll notice that you've got two green rods. One is lighter green and one is a dark green. A lighter green we refer to simply as green. And then the darker one we call dark green. Starting out, we want to determine the factors of 8. You'll notice that the brown rod is 8 units long. We're going to make single color trains to measure this rod. I'll show you what we mean. To measure this rod with the white, which is our unit, we just place them side by side, and you can count and see that there are 8 white rods there. We can also measure the brown rod with reds. Place your red rods end to end until they're the same length as the brown rod. We're going to continue doing this. When we try to use the green rod, we see that 2 of them is too short, but 3 is too long. That means that we are unable to measure the brown rod with the green rods. Moving on to purple, we can measure the brown rod using 2 purple rods. And we find out that there are no other combinations of single color rods that will measure the brown rod. Think about the lengths of these. The white rod is 1 unit long, the red rod is 2 units long, and the purple rod is 4 units long. The brown rod is 8. This tells us that the factors of 8 are 1, 2, 4, and 8. Students need to recognize that a number is a factor of itself. I want you to try this on your own. So pause the video while you do this. I want you to find the factors of 9 by making single color trains. And then I want you to find the factors of 10 using single color trains. The blue rod is 9 units long, and the orange rod is 10 units long. So for each of these, you'll be starting with these rods. Pause the video while you complete this. Did you find that the only factors of 9 are 1, 3, and 9? For the factors of 10, you should have found 1, 2, 5, and 10. I hope you were able to complete this without any trouble. Let's look at the definition. We're defining greatest common factor here. Let A and B be whole numbers, not both 0. The greatest natural number d that divides both a and b is called their greatest common factor. And then you can see the notation here. GCF is the greatest common factor, and we write greatest common factor and then place our two numbers in parentheses. We're going to use the Cuisenaire rods to find the greatest common factor. I want to find the greatest common factor of 12 and 16. Now the rods in your kit are not long enough for this, so we make rods that are these lengths. To make 12, I'm using the orange rod and the red rod. And then I make one that's 16 units long as well. I'm going to complete this like we did in the previous exercise. I'm going to find all the factors of each one of these numbers by making single color trains. So for 12, I can see that the white rods measure 12. The red rods do also. The green, the purple, and the dark green. Let's move on to 16. I can measure 16 using the white rods, the red rods, the purple rods, and the brown rods. You can see we're doing the same thing that we did in the previous exercise. To find the greatest common factor, I want to find the longest rod that is used for both of these. As you compare, you'll notice that white, red, and purple were used in measuring the 12 and also the 16, but the purple is the longest one. This is the one we're looking for. The length of purple is 4, so 4 is the greatest common factor of 12 and 16. I want you to do this on your own. I want you to use the Cuisenaire rods to find the greatest common factor of 6 and 8. So pause the video while you do this. Were you able to successfully complete this activity? Did you find that the greatest common factor of 6 and 8 is 2? That's the red rod. We're going to look at some other methods for finding the greatest common factor. One way that we can do this is to list all of the factors of each of the numbers and compare our lists. We want to find the greatest common factor of 18 and 24. I'll write out all of the factors of 18. Think of it like this. 18 is 1 times 18, 2 times 9, and 3 times 6. So I have all of my factors when I think of it like this. When I think of the factors of 24, 24 is 1 times 24, 2 times 12, 3 times 8, and 4 times 6. I have 8 factors there. After I've written out all the factors, I look for the largest number that is in both lists. When I compare my lists here, I see that 6 is the largest number in both. So that's the greatest common factor of 18 and 24. So notice how I write this. GCF of 18 and 24 is 6. Another way of finding the greatest common factor is to write out the prime power factorization of each number. We talked about the prime power factorization in a previous lesson. Let's look at the pair of numbers 120 and 150. I'll need to find the prime factorization of each of these numbers, and I'm going to do that using the stacked short division process that we talked about in a previous lesson. Study what I've done here. After I've completed the process, I'm able to write the prime power factorization of each of these numbers. 120 is 2 to the third power times 3 times 5, and 150 is 2 times 3 times 5 squared. In order to find the greatest common factor from these factorizations, I look for the prime factors that are common to both. I notice that both of the prime power factorizations use 2, 3, and 5. For each of these prime numbers, I pick the one that has the smaller power. So for instance, when I'm looking at the prime number 2, I've got 2 to the third power and 2 to the first power. I pick 2 to the first power because 1 is smaller than 3. Both of the prime factorizations contain 3 to the first power, so I just use 3 to the first power. And comparing the prime number 5, I've got 5 to the first power and 5 squared, so I'll pick 5 to the first power. I multiply these together to give me my greatest common factor. 2 times 3 times 5 is 30. So the greatest common factor of 120 and 150 is 30. Let's look at another example so that you can understand more fully what's going on here. This time we're finding the greatest common factor of 4,455 and 9,450. You may notice on the screen that I have listed this as greatest common divisor. The greatest common divisor and the greatest common factor are the same thing. I want you to verify the prime factorizations that I have here. I found that 4,455 is 3 to the fourth power times 5 times 11. 9,450 is 2 times 3 cubed times 5 squared times 7. To find the greatest common factor, we look for the primes that are in both lists. Both lists contain the prime number 3 and the prime number 5. These are the ones I'll focus on. Remember, I take the one with the smaller exponent. So comparing the prime number 3, I have 3 to the fourth power and 3 cubed. I'll choose the 3 cubed since 3 in the exponent is smaller than 4. I also do the same thing with the prime number 5. I have 5 to the first power and 5 squared. So I pick 5 to the first power since that one is smaller. I then multiply these together to get the greatest common factor. 3 to the third power times 5 is 135. This is the greatest common factor of 4,455 and 9,450. Again, notice that I only use the prime numbers that are in both lists. Here's one more method that we're going to look at. This is the Euclidean algorithm. We may need to review the terminology here. Using the Euclidean algorithm, notice here in the first part of this problem, I've got 1,539 here outside the bracket and 3,144 inside the bracket. 1,539 is the divisor. 3,144 is the dividend. 2 is the quotient, and then the remainder is 66. You're not going to worry about the quotient, but notice how the remainder, the divisor, and the dividend behave throughout this process. You do your normal division here, right? Then in the next step, the divisor becomes the dividend. And the remainder from the previous step becomes the divisor. We divide normally again. Notice as we move down that, again, the divisor becomes the dividend. So 66 moves into the dividend spot. The remainder now becomes the divisor. And we keep going. We keep going until we get a remainder of 0. The greatest common divisor, or the greatest common factor, is going to be the last non-zero remainder. So in this problem, our greatest common factor is 3. What is it the greatest common factor of? It's the greatest common factor of 1,539 and 3,144. I'd like you to try this method on one of the previous examples. You have the greatest common factor already, so you'll know whether you get it right or not. So make sure you follow the trail of where the divisor goes, where does the remainder go, and think about all of that and how those things are moving around in the problem. It's a very interesting process, and it has historical significance as well. We're going to move on to the least common multiple. Here's the definition of least common multiple. Let A and B be natural numbers. The least natural number, m, that is a multiple of both A and B is called their least common multiple. And we use the abbreviation LCM to designate the least common multiple. Notice our notation there. We're going to go back to the Cuisenaire rods and look at how we can find the least common multiple using Cuisenaire rods. We want to find the least common multiple of 3 and 5. The green rod is 3 units long and the yellow rod is 5 units long. I'm going to build single color trains until they are the same length. You can see here that I've added green rods and yellow rods, and now these are the same length. I can take my white rod, which is 1 unit, and measure this to see how long it is. And it takes 15 of the white rods to reach the same length. So I know that the least common multiple of 3 and 5 is 15. Here's another example. We want to find the least common multiple of 6 and 8. Again, I make single color trains, and I stop the first time they become the same length. I can take my white rod and measure this, and I see that it takes 24 of the white rods. So I know that the least common multiple of 6 and 8 is 24. Another way of finding the least common multiple is by listing multiples of each number. Let's look at an example. We want to find the least common multiple of 6 and 10. The multiples of 6 are 6, 12, 18, 24, 30, 36, and so on. The multiples of 10 are 10, 20, 30, 40, 50, 60, and so on. We want the smallest number that appears in both lists. You'll notice that there are at least 2 numbers that are in both lists. We want the smallest. 30 is the smallest number in both lists, so 30 is the least common multiple of 6 and 10. So we write LCM, put 6 and 10 in parentheses, and this equals 30. Another way of finding the least common multiple is to look at the prime factorization of each number. Let's find the least common multiple of 90 and 165. Again, we have to find the prime factorization, so I've already done this for us. The prime power factorization of 90 is 2 times 3 squared times 5. The prime power factorization of 165 is 3 times 5 times 11. You can verify this with a calculator. When we find the least common multiple, we use every prime that we see there. So we have 2, 3, 5, and 11. We have 4 different primes here, and we have to represent each one of these. When one is repeated, we make sure that we choose the one with the larger exponent. So 3 is in both lists. We have 3 to the first power and 3 squared. We need to choose 3 squared because that exponent is larger. In both lists, I have 5 to the first power. So I just write down 5 to the first power. My least common multiple is the product of all of these. So I have 2 times 3 squared times 5 times 11, which is 990. The greatest common factor and the least common multiple are useful in many areas of mathematics, in particular when we complete some mathematical operations. The greatest common factor is used when we simplify fractions. When we find a common denominator, we use the least common multiple. These are some basic examples of when we use these. We also have a fact here that shows the relationship of the two. The greatest common factor of A and B multiplied by the least common multiple of A and B is equal to the product of A and B. Using a little algebra, if you know one of these, you can find the other one. For instance, if you know the greatest common factor of A and B, you can use your algebra processes to find the least common multiple without going through other methods. Make sure that you practice finding the greatest common factor and the least common multiple using all of these methods. Remember, when you start teaching, some students may be able to learn one method easier than another. When you have different methods to show students, it increases your chances of reaching all of your students. And that's our goal as teachers. Again, the images that I had in this presentation of the Cuisenaire rods were produced at the website brainingcamp.com.